Welcome to section 7.5, modeling data, y'all. This is Mr. Bergman, your boy, right here. We got. Let's review. We've got because although this section does contain a lot of stuff that we've actually done before on these projects that I've been assigning, like the SAND project and the strobe light project, we've got a little review to do. So what is the linear equation y equals mx plus b that passes through these points? If you get this point here and this point here, you can find the rise and the run and divide them. -6 divided by 3 will give you -2, which is the slope. And here, or you could do y2 minus y1 over x2 minus x1 to also get the same exact slope. Either way, the slope is -2. Then you can also look at this point right here, and if it's actually, we're kind of lucky. The math is a bit easier because one of the points is the y-intercept, so you can say that the y-intercept is 6. B equals 6 right here. B equals 6. Texting versus exercising. The scatter plot shows time spent texting, x, and the time spent exercising, y, by each of the 25 students last week. Write an approximate equation of the line of best fit for the data. It doesn't have to be the exact line of best fit. Well, we know that if we had this data on Desmos, we'd be able to force. We'd be like, all right, Desmos, we got all this data, and I want you to find the constants, m and b, that would make the line as close as possible to all the data. Go, Desmos, do it. But we're going to do that by hand here. We're going to kind of like artistically line it up, give it an eyeball. Yeah, this looks good. And Alex.com is actually not going to be too picky when it comes to exactly what where we put these points and what line gets produced by them. Where it is going to be picky is whether or not you correctly, whether or not you round or not, which is kind of odd to me. It's not great programming, and I don't like this question a whole lot from that standpoint. So my pro tip right here, my Alex pro tip is this: choose a decimal slope with no rounding, and if you can do the intercepts, that's even better. Because check this out: if you have a slope of 0.5, no rounding. If you have a slope of 0.25, no rounding. If you have a slope of 1/3, then you're not actually, I believe you're not actually allowed to type in a fractional slope. You have to round it to decimals, 0.3333. Repeating would be perfect, but you got to round it somewhere. So you could, if you typed in 0.33333, which is not equal to 1/3, then it will mark you wrong because you had to round. 0.333 is not equal to 1/3, so that's why Alex will mark it wrong, which is a little frustrating. So choose some, make it easier on yourself. Make the slope -1, or make the slope -1/2, or -1/4. Not anything you'd have to round. In any case, I chose the intercepts here, and that makes it a lot easier. So you got 10 up here, and you can see the rise. The rise is -10, and the run is 10. Easy to see because they're intercepts, and so therefore the slope is -1. No rounding involved. The y-intercept is 10, so that's why the b value here is 10. B, use your equation from part A to predict the time spent exercising for a student who spends 4 hours texting. Well, because I made my life a bit more computationally, a bit more easy, we can actually put this in y equals -x. It's like not like it would be terrible to have to try and do y equals -7/6 x. It's just a lot easier with -1x plus 10 from an Alex standpoint. So we say that x equals 4, get that from the information, and graphically you could say, oh, x equals 4, go up to the line and say, oh, the y is equal to 6. Or you could numerically use the equations y equals negative, and the input is 4, so make it -4 plus 10, and then you add, you get what's down here. I'll leave it to you to see the answer there. Now, when it comes to answering another Alex question, there's types of relationships. And y'all know as teenagers, people get together as all kinds of relationships, and that's great. There's sometimes two people, they have absolutely no relationship whatsoever. It's all very scattered. It's all over the place. The coefficient of correlation is a measure of how close that data is to a line or a curve. So if you were going to try and draw a straight line through all this data, you really couldn't. And if you tried, it would be just a terrible fit. So the R value would be 0. However, here we've got positive linear relationship. The correlation of coefficient R is positive. Things are looking up between x and between y on this data. we got the data we have on this relationship is that there's positive linear growth here going on. So things are looking good. And so it might even be close to 1 or equal to 1 if they're all perfectly on a line with a positive slope. Now the relationship going here, it ain't going so well. Things are going down. Things are trending poorly. So the R value is going to be -1. Or in this case, looking at this particular set of data, there's not perfectly on a straight line, but it's going to be close to -1. And so that's what that looks like. Now you might remember from the SAND project or from the parabola project or from any Desmos regression, it gives you an R squared value. It doesn't give you R value. The difference between R and R squared is that it's just squared. Like R times itself is R squared, just like X times itself is X squared. So if you got a 0 before for R, 0 times itself is 0 in R squared. If you got a -1 for R, then R squared is going to be +1. So R squared will never be negative, just like X squared will never be negative, assuming it's all real numbers. So the coefficient of correlation, I think we're much more familiar with this from the SAND project and parabola project and all that. And another measure of how close the data is to a line or to a curve. So you can see here, this data is, it's not a straight line, but it does kind of look like it could be on a parabola. So it's nonlinear relationship because it's a parabola, and the R squared value is going to be close to 1 because it does kind of look like a parabola. Things were going down, but you know what? In the data, they turned it around, and now things are going back up again. And so things are kind of hopeful in this relationship. The exponential curve right here is nonlinear. We recognize this now that we've done chapter 7. We recognize this as an exponential curve. You won't see the word exponential on alex.com. You'll just see the word nonlinear. Is it a line or is it not a line? Well, it's not a line, but the pattern is close, and we can see that the R squared value is going to be close to 1. Very close to a perfect relationship. Things are really going well for this data set. It's going up. I wanted to talk now about this next page because this next page is going to help you on the final exam. Let's talk about the final exam. The final exam is going to be a project. It's not going to be a test. It's going to be a very expansive project. You might remember in the SAND project, I asked you to choose between quadratic, cubic, and quartic curves, and the answer was it was a cubic curve. Well, for the final exam, it's going to be very similar. Here are all the parent functions that we have talked about already. We've talked about, now that you remember the square root curve and the cube root curve from chapter 6, the cubic curve from chapter 4. Well, we're going to do chapter 9, and we're going to learn about these curves too. And then on the back, you'll see, we just finished chapter 7. There's the exponential curve. You notice the base E. And then the logarithmic curve here we learn about after we do our chapter 7 project. Well, there are 10 of these parent functions, and so I'm going to give you a project, you'll walk into the room. I'll say, hi, welcome to the final exam. I hope you do well. And then I'll give you an event, and you'll have to analyze the data, and the event will be either cubic or quadratic or cube root or inverse square or exponential or logarithmic in nature. And it'll be your task. It'll be one of these 10 parent functions. And you'll have this sheet here. You will, in fact, be able to have, it's an open note final exam. It's an open internet final exam. You'll have all the internet at your disposal and all the notes that we've ever done at your disposal, and you'll have your laptop as well. So that's good, and I hope it's helpful, and I hope it simulates what you actually have to do when you do math in the real world. Every indicator that I have about how people really use Algebra 2 in the real world, it all has to do with crunching data and in teams where the internet is available, and finding some sort of a pattern and making a prediction. Like that's the Algebra 2 version of what you might have to actually do in the real world for a lot of this stuff. So that's how I model my final exam. And so it'll be your task to choose one of these curves, and don't worry too much if you choose the wrong one. You can still get a pretty good grade as long as you back up your choice with a lot of like, okay, so here's my wrong curve, and then here's the intercept. Oh, good. If you use the wrong curve and find the right intercept and find the right and you describe it well, like the domain and the range and all that, then you can still get a pretty good grade. But there is a right answer to and a wrong answer to which parent function is it. Anyway, the reason this the worksheet is here is because I wanted to go through what it would look like to type it into Desmos. So let's say you might remember in the cubic in the SAND project, it was a cubic curve. The parent function is y equals x cubed, and if you wanted to allow the Desmos to dilate this, you would have to put an a out in front. That's a vertical dilation. If you wanted to allow for a vertical shift, you can add a plus k on the outside over here, plus k. And if you wanted to allow for a horizontal shift, you would add an h, minus h on the inside. So this is the formula for a standard, like the vertex form of a cubic, or it's not exactly called vertex form, but this is what it could look like here. So with vertical dilation, vertical shifts, and horizontal shifts. So if you wanted to type that into Desmos, the regression would look like this. y1 is approximately a times x1 minus h cubed plus k. You'd be saying, basically, I've got all this x1 and y1 data, and now I want you to force a, h, and k to be as close as possible to all my data. What's the best possible a, h, and k values you could have so that my cubic curve fits as close as possible to the data that I have, which I believe is cubic in nature. That was the SAND project in a nutshell. Now, so let's take a look. We've got, in this next upcoming project in Chapter 7 or on the final exam, I could be giving you exponential data in nature. So the parent function is y equals e to the x. And I know that might still feel a little bit awkward to have a number, an irrational number like pi or like e as a base. But that's just what we're going to do, because the more we do it now, the less awkward it'll feel later. Y equals e to the x, and then with a vertical dilation, you can have c out in front, with multiplication. With a vertical shift, you can have plus d here. And then I'm going to say that you can have a horizontal dilation as well, and I'm going to introduce a k constant here. Now, if you remember from the word problems that we were doing, that the rate of, the interest rate would be exactly where you would put k. So we're going to put a horizontal dilation. We're going to allow Desmos to horizontally dilate things. So you can say, Desmos, I've got all this x1, y1 data. Give me the c, k, and d values that are as close as possible, that allow this exponential curve to, as close as possible, fit my data, which I believe is exponential in nature. So there it is. Choosing parent functions. This is a worksheet that you're going to need to carry with you from now to the end of the year, and definitely have at the forefront of your notes when it comes to taking the final exam, preparing for the final exam. So keep this. Make sure you know where it is, and we'll talk more about it tomorrow in class. So take care. Thanks for sticking around, and I'm going to say on a personal level that my favorite action movie of all time is The Matrix from the 90s. And I know I'm dating myself, but I think it's the greatest action film of all time. Prove me wrong. I'll see you in class.